Okay, let's spend some time about proving theorems about lines and angles. So some of the stuff that we're going to talk about in this lesson is going to be really important when you're doing your proofs throughout your Edmentum class. So in this lesson, we're going to prove theorems about lines and angles, including angles formed by a transversal, that's a line like this, that crosses parallel lines and then points on a perpendicular bisector. So the defining property of parallel lines is that they never intersect one another. So in addition to them not intersecting, just for like the piece that you see, these two will never touch, right? This one's going to continue to go on, and they will never get closer or farther apart. So that's one defining property of parallel lines. Now, a transversal is a line that intersects two or more lines in the same plane. So here, this is my transversal T. And then R and S are parallel. So we can remember that we can mark parallel lines using our little arrows. So R and S, here, my picture's a little blurry, but R and S are parallel. So in the diagram, my transversal T crosses parallel lines R and S. Now when a transversal crosses two parallel lines, we have some special angle pairs that are formed. My first one are my interior angles. That lie between the two parallel lines. So that's going to be my angles 3, 4, 5, and 6. I'm going to highlight 3, 4, 5, and 6. These are my interior angles. That's these angles on the inside. So interior, inside. You can see that they're kind of inside of the parallel lines. Now my exterior angles lie outside of the two parallel lines. That's my angles 1, 2, 7, and 8. We have 1, 2, 7, and 8. All right, and they're on the outside of my parallel lines. So you can see my inside of my parallel lines, and then the outside is anything outside of there. Now, corresponding angles are angles that are in the same relative position between the different intersections. So my corresponding angle pairs in the diagram are going to be 1 and 5, 2 and 6. We have 7 and 3, and then 4 and 8. So you'll notice that for my corresponding angle pairs, they're going to be the same in the same position. So 1 is in my top left of my first parallel line, and 5 is in my top left of my second parallel line. So we can see that those two are corresponding. Now 2 and 6, those are both in the top right. My 3 and 7 are both in the bottom left. And then my 4 and 8 are both in the bottom right. And so you'll see that they're in that same position for each of those parallel lines. But they are on different parallel lines, right? So 5 and 6 are not corresponding because they are attached to the same parallel line. All right. So, talking about those corresponding angles, we can do the corresponding angles theorem. So the corresponding angles theorem tells us that if two parallel lines are cut by a transversal, then the corresponding angles are congruent. And remember, for congruent, we use that weird little symbol. It looks like an equal sign with a little squiggly on top. That's my congruent symbol. So then we have this question. It says that lines M and N are parallel, so we can always mark them with those little arrows. So we know that they're parallel, and then they're intersected by this transversal line L. And so now it says, since the measure of angle 1 is equal to 71 degrees, then the measure of its corresponding angle, M something, is also 71 degrees. So I know that corresponding angles should have the same measurement. Now I just need to figure out which one that is. This one is the top left of this area. So then that means that its corresponding angle must be 3, because that's also in the top left of its little group. So then we can say that the measure of angle 3 is also 71 degrees. Now let's look at alternate interior and exterior angles. My alternate interior angles are the angles diagonal to each other inside the two parallel lines. So my alternate interior angles in my picture here, remember that they're going to be inside, so I'm just looking at these four angles inside. That's going to be this angle 109 and this one. Those are my alternate interior angles. And I have this other little group, my 71 degrees. So those are my alternate interior angles. They're inside my parallel lines. And alternate means that they're opposite. So you can see that they're opposite of one another inside those parallel lines. So if two parallel lines are cut by a transversal, then my alternate interior angles are congruent. And we can see that from the picture because I can see that my alternate interior angles have the same measure, and these two alternate interior angles also have the same measure. So if two parallel lines are cut by a transversal, just like these two are, then we can say that their alternate interior angles are congruent. Now let's talk about alternate exterior angles. Similar, but now we're looking at the angles outside. So alternate exterior angles are the angles diagonal to each other outside my two parallel lines. So here I have this picture. My M and my N are parallel, so I'm going to mark them so I know. And then my alternate exterior angles are the angles diagonal to their outside. So that's going to be like this 109 and this 109, and then my two 71s as well. So this 71 and this 71. And you'll notice that I'm not looking at this stuff on the inside. These guys are also congruent, but I'm just focusing on my alternate exterior angles, outside and opposite of one another. So my alternate exterior angles theorem says that if two parallel lines are cut by a transversal, then alternate exterior is outside, then my alternate exterior angles are congruent as well. All right, so now we have a little bit of a proof here. It says, given that lines R and line S are parallel and cut by transversal T, we need to prove that 1 is congruent to 8 and 2 is congruent to 7. So I have this R and this S, these guys are parallel. I need to prove that this one is congruent to this one, and my 2 is congruent to my 7. So those are the two that I'm looking at. I always start with my given. So my given is that lines R and S are parallel and they are cut by a transversal T. That is my given. I'm going to say that 1 is congruent to 5 and 2 is congruent to 6 because those guys are corresponding angles. So that is by the corresponding angles theorem. And that's the first one that we talked about in these notes, my corresponding angles. Now I can say that 5 is congruent to 8 and 6 is congruent to 7, and that's by my vertical angles theorem. Vertical angles theorem we learned in a different set of notes, so make sure that you know that anytime angles are sharing two lines and they are directly across from one another, they are congruent. And it could be even more than that, right? So if I have some lines like this, my vertical angles will still be congruent. And so as long as they're all kind of sharing this one point, any angles directly across from one another will be congruent. And then lastly, we're going to say that 1 is congruent to 8 and 2 is congruent to 7. And you can see in here, 1 is congruent to 5 and 5 is congruent to 8. And then 2 is congruent to 6 and 6 is congruent to 7. So anytime I see something like that where they're both congruent to the same thing, that is going to be the transitive property. So this is the transitive property of congruence. So my transitive property of congruence says that if something is congruent to something else, and that thing's also congruent to a third thing, then these two guys have to also be congruent. And that's from a long time ago. I think that was all the way back in Unit 1. So the transitive property of congruence says that these two are congruent to one another. All right. So this one, It's another question. It says that lines M and line N are parallel, and they are intersected by this transversal line L. So again, I'm just going to mark that they're parallel. That's just for me to remember. And I need to prove that 2 is congruent to 7, and 6 is congruent to 3. So I'm looking at my alternate interior angles. So again, I'm going to start with what I'm given, that they're parallel and cut by a transversal T. That's given. Now my corresponding angles theorem is anytime it matches with like the same top left to top left, bottom right to bottom right. And so 2 is going to be congruent to 4 because of my corresponding angles theorem, because they are both in my top right. And 6 is going to have to be congruent to 8 because they are both in my bottom right. And that's because of my corresponding angles theorem. Now my vertical angles theorem, remember, is anytime they're just across the same point. And so 4 over here is going to have to be congruent to 7. Those are my 2 vertical angles over here. And 8 is going to have to be congruent to 3 because those are also vertical angles. And then lastly, just like the last one, my transitive property of congruence says that if 2 is congruent to 4 and 4 is congruent to 7, then 2 must also be congruent to 7. And same thing over here. If 6 is congruent to 8 and 8 is congruent to 3, then 6 must also be congruent to 3. So that last step is my transitive property of congruence. So my same side interior angles are a little different. My same side interior angles are interior angles, which means they're on the inside. So they are on the same side of the transversal. So I can see my transversal here. These 2 lines are parallel because they're marked. This is my transversal, and these 2 are on the same side of the transversal. They're not on the alternate sides like our other ones that we've been looking at. And they're both on the inside, which means that they are the same side interior angles. So if 2 parallel lines are cut by this transversal, then the pairs of the same side interior angles are supplementary. Remember that supplementary means that it equals 180 degrees. And so if I look up here, I can say that 109 degrees plus 71 degrees is equal to 180 degrees. So that's true. So if I add these 2 angles up, I should always get 180. Okay, so now let's look at this proof for same side interior angles. It says that lines R and S are parallel. I'm just going to mark them. And they're cut by this transversal T. And I need to prove that 4, which is this one, and 6 are supplementary, which means they're going to add up to 180 degrees. So my given is that I have these 2 parallel lines and they're cut by a transversal. Now I can say that 2 up here is congruent to 6 by my corresponding angles theorem. Remember, corresponding angles, they're both in the top right, so I can say that they are congruent to one another. Now I then know that the 2 measurements are equal because that's my definition of congruence. If 2 angles are congruent to one another, that means that their measures are equal. I can also say that 2 and 4 are supplementary, so 2 and 4 are over here, and that's going to be based on my definition of a linear pair. So remember, my linear pair angles are 2 angles that if I added them together, they would make a straight line, and so I can see 2 and 4 would totally make a straight line. They're both together, they're attached, and they make a straight line there. So that's my definition of a linear pair. That then means that 2 and 4 must be 180 degrees, because that's going to be my definition of supplementary. Remember that all linear pairs are supplementary, which means they add to 180 degrees. Now, this says that the measure of angle 6 plus the measure of angle 4 is equal to 180 degrees. And so you'll see that I substituted the measure of angle 6 in for the measure of angle 2, and that's because up here I proved that they're equal to each other. So if I prove that they're equal to each other, I can substitute one in for the other. And so I just took this equation, I replaced my measure of 2 with my measure of angle 6, and that's going to be my substitution property of equality. And then my very last step, that means that 4 and 6 must be supplementary because of the definition of supplementary. And the definition of supplementary says that two angles will add to 180 degrees, which we just said right here. Okay, so now we have this question. It says that lines M and N are parallel to one another and they're intersected by this transversal line L. So it says if the measure of angle 6 is 64, then the measure of angle something plus another something should be 180 degrees because same side interior angles are, and that's going to be supplementary. And so I'm going to figure out which one is supplementary because of same side interior angles. If I'm looking at angle 6 here, well then I know that my same side interior angle is going to be this angle 7. So then that must mean that the measure of angle 6 plus the measure of angle 7 is 180 degrees. And if my measure of angle 6 is 64 degrees, that means that I can take 180 degrees minus the measure of angle 6, and I will get the measure of angle 7. In this case, that would be 116 degrees. So then I will say that the measure of angle 7 is 116 degrees. And then very last page, I know that these notes are a little bit long. So last we're going to look at some perpendicular bisectors. So my perpendicular bisector theorem says that if a point lies on the perpendicular bisector of a line segment, then the point is equidistant from the endpoints of the segment. So equidistant might be a word that you don't really know too well. Maybe you haven't heard it before. Equidistant means equal distance, which makes sense. It's kind of in the word equidistant, equal distance. So we can say that any of these points along my perpendicular bisector, they're going to be equal distance from each endpoint. So we can see that this line is congruent to this line is congruent to this line is congruent to this line, right? So if I have these points along my perpendicular bisector, they will always be the exact same distance from each of my endpoints. Now in order to prove this, we can look at this diagram. We have XY, which is this vertical line here, is a perpendicular bisector of AB, which is this line segment here. We can create some triangles, so we have AOX, which is this triangle up here, and BOX, which is this triangle up here. And they are both right triangles. Since XY is perpendicular to AB, that means that these angles in here are right angles. So we have two right triangles on the top here. Now we're going to use that distance formula, and we know that AX is going to equal BX because they're both going to equal 5. A little refresher about my distance formula. Remember that my distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. So this is my distance formula. That's what they're using. Now in your tutorial you can see these points a little bit better. They're really, really blurry on mine. But if you look at these 2 points, you can plug those points into my distance formula and you would get 2 5s for both of those. Now since the lengths are equal, we've successfully shown using coordinate algebra, which is where we're using this coordinate plane, that the perpendicular bisector theorem holds true, which says that they are always going to be equidistant from the endpoints. So we just proved that there. Now we have this last question. It says, what is WZ, so that's this point right here, this line, if WY is perpendicular to WZ? So I want to figure out what is WZ if, WY is perpendicular to XZ. XZ is this line here, WY is this line here, and I know that they are perpendicular. It makes a little right angle there. So I want to figure out what this line length is. So we can use the perpendicular bisector theorem. It tells us that if a point lies on the perpendicular bisector of a line segment, then it is going to be equidistant or equal distance So equidistant from the endpoints of the segment. So since we know that WX is 7.25, that means that WZ must also be 7.25, because this point W is going to have to be equal distance from each of my endpoints here. So these two must be congruent to one another.